Physicists calculate protons' pressure distribution for the first time. This I found in phys.org. Physics stands for physics, of course. And this is written by Jennifer Chu from the Massachusetts Institute of Technology. And of course, we all know that's a super prestigious, worldwide famous institution. So everything they publish must be right. Well, people pay more attention to it, I guess. That's what is normal for us. So let's take a look at this article and see where our critical minds lead us. Well, this is the first thing they show us, which is MIT physicists have calculated the pressure distribution inside a proton for the first time. They found the proton's high pressure core pushes out while the surrounding region pushes inward. And that's, of course, credited to MIT. If you look at this, this is, I guess, the proton. They're mapping it. I see vectors. Vectors have an arrow. The purple area has vectors going clockwise. And those vectors, of course, I guess bigger means stronger. And then as you get inward, you see they're going counterclockwise. And so you obviously are thinking, well, there's spin. Whatever's inside is spinning around in some way. But I thought protons were made out of quarks. So how is this possible? Well, I'm not even sure what they're measuring. So again, I'm using this as a critical mind going through this article. That's what I'm here to do, to help you out. And it says, for the first time, physicists have calculated protons' pressure distribution and found that the particle contains a highly pressurized core that, at its most intense point, is generated greater pressures than are found inside a neutron star. Of course, neutron stars have immense pressures. I don't know, something like, a teaspoon weighs as much as a bunch of moons of ours or something. The core pushes out from the proton center while the surrounding region pushes inward. Imagine a baseball attempting to expand inside a soccer ball, then collapsing. The competing pressures act to stabilize the proton's overall structure. Now, pressures of what? Again, what's expanding? What, again, they're made out of, supposedly they're made out of quarks. And quarks, of course, mean it's one thing, but I guess it's a family. I've talked about that already. The physics results published today in Physics Review Letters, of course, that's another prestigious publication, represent the first time that scientists have calculated a proton's pressure distribution by taking into account contributions of both quarks and gluons, the proton's fundamental subatomic constituents. Okay, those are fundamental subatomic. That means there must be more, but quarks and gluons. Now, if you know this channel and you know me and you know people like my friend Dr. Alexander Unsker, we believe you have to throw out all of particle physics, at least from 1930 on, the neutrino, the Z particle, the W particle, the quarks, the Higgs bosons, because the way they find them. So again, if you're a critical thinker and you've read a lot about this stuff, you're not believing that. So, but anyway, so it's interesting. They do an experiment. So let's take a look at that, because maybe we can use that for our own work. Like my father and I have a particle model. Other people have ether models. Other people have lattice models. That's why you want to read these things. Pressure is a fundamental aspect of the proton that we know very little about at the moment, says author blah, blah, blah from MIT. Now we've found that quarks and gluons in the center of the proton are generating significant outward pressure, and further to the edges, there's a confining pressure. I just don't know what that means, because are they moving around? Are quarks particles? Are quarks waves? Again, there's just no physicality, and without physicality, this all means nothing, folks. You can say this all you want. It's a picture. I mean, you go back to this picture again. It's a picture. That's all it is. And they're talking about all this stuff and pressures and all that, and mathematical and the model and anyways, we found gluons, all right, that's fine, confined to pressure. With this result, we're driving toward a complete picture of the proton structure. It isn't complete, folks. I mean, we say it's made. If you just go look up quarks alone. Just go on to Wikipedia and look up quarks. The picture they have is a round, perfectly round circle with perfectly round other circles, smaller ones, and they call those quarks. Now they're talking about we're getting a complete picture. Well, what they actually are getting, and we'll see later, is they are firing electrons at a nucleus, and they're getting some data back. But all this complete pictures, according to them, using particles that we say don't exist, because they've sort of invented them. So this is all like a house of cards. But if you're reading along, it sounds like, oh yeah, of course, we're getting a complete picture. Again, is this the picture, or is this the picture that we have on Wikipedia, which is a circle with other circles in it? What do we have? It's getting confusing now. Anyways, remarkable quarks. There you go. In May 2018, physicists of the blah, 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 Thomas Jefferson National Accelerator Facility announced that they had measured the proton's pressure distribution for the first time. Okay, now this is interesting. Now this is worth reading the article. Using a beam of electrons that they fired at a target made of hydrogen. Okay, because obviously it's a very uncomplex atom. The electrons interacted with quarks inside the protons in the target. They did if you say you did. Now you see how that is. Now as a critical thinker, that's the way you got to think. If you're a person like me who wants to say, look, quarks, they're just totally suspect the way they came up. I mean, the whole system of it. Again, look up dissident science quarks. I think you'll hear me talk about this. But again, even if you haven't, the idea is that you have to believe that these things all exist. And then after you believe that, then you're going to say it's interacted with quarks inside the proton. Well, if protons are made of quarks, then it's not inside a proton. It's quarks. It'd be like saying, well, we shot an arrow at this target and it hit, the atoms. Yeah, of course it hit the atoms. Yeah, it hit the atoms if you think they're made out of atoms. But if you don't think they're atoms, you hit the target and it's made of this, made of that. But it's the same way. So if it's something, when you hit the target with an arrow, it's really hitting atoms. It's not hitting paper. And the same size here, same thing here. A proton, if it's made up of quarks, you're hitting quarks. It's not inside a proton. The quarks that make up a proton, maybe. Again, look at the language. Look at the way they talk about these things. Like this is where Alexander Unsker talks about arbitrary packages with arbitrary attributes. There we go. It's a perfect example. Physicists then determined the pressure distribution throughout the proton based on the way in which the electrons scattered from the target. Now, of course, think about it. They're hitting quarks. Are quarks moving? What are quarks? Are they really particles? Are they waves, like in a Jeff Yee theory? Or what are they? And if they're coming off of that, and how do we know? We don't even know what is there. I mean, the truth of the matter is we're shooting electrons at a nucleus. That's all we're doing. Now, all this other stuff is stuff built on stuff, a house of cards built on a house of cards built on a house of cards, if you ask we critical thinkers outside the mainstream. And so, again, what I would say is interesting here is that some people are doing that, and can we get the data from them? And then one of the ideas is, can we, if we got a gajillion billion of these paths, let a machine learning algorithm go and see if it finds patterns from these. Okay, it's not going to tell us what the world is made out of, but it will certainly tell us more than us saying that we already believe there are quarks, which we invented, and there are gluons, which we invented, and those things, of course, we're hitting them, of course. The results show a high pressure center to the proton that is the point of the highest pressure, measured to about 10 to the 35 pascals, or 10 times the pressure inside a neutron star. However, Shannon says that the picture of the proton's pressure was incomplete. They always say that because this is another tactic they always use in these articles and in particle physics. What they use is they always say, oh, but we don't know everything, so we already forgot. Okay, oh, that's sort of in our mind does a psychological trick, and that says, oh, what they're saying must be true because look, they're questioning what they don't know everything. So that's one of the things. Every time you read an article about this, you have to think, oh, the future. We don't know everything. Well, let's put it this way. We don't think even quarks exist, so we're just shooting electrons at the nucleus. They found a pretty remarkable result, but that result was subject to a number of important assumptions that were necessary because of their incomplete understanding. Yeah, think. I like that. That's my favorite. Yeah, think. It was an assumption. Yep. You got that right. And it was necessary based on an incomplete understanding? Yep, you got that right. Specifically, researchers based their pressure estimates on interactions of proton's quarks, not its gluons. I guess I get, this is like for me and people who have studied all this stuff and realize we have to throw it out and start over. This is just like reading about the unicorns world to see what, this is sort of like reading the flat earth people who are actually pulling everybody's leg, right? And now they get real followers, but the people who started it are really pulling everybody's leg. And you start to read all these things and you just laugh. I mean, because it's funny, it's the quarks, not the glue. It's like saying, well, in the unicorns we found, we hit their horns, but not their hoofs. That's what we're, and unicorns don't exist. Protons consist of both quarks and gluons, which continuously interact in a dynamic and fluctuating way in the proton. What does that mean? Let's face it, we have no idea. Besides of making them up, we have no, look at that sentence. Protons consist of both quarks and gluons, which continuously interact in a dynamic way, in fluctuating way. That was worth the entire, just to get to that sentence, to show you the idiocy, the hypocrisy of all this. The Jefferson lab team was only able to determine the contributions of quarks with this detector, which Shannon says leaves out a large part of the proton's pressure contribution. I can't believe they do this with a straight face. Over the last 60 years, we've built up quite a good understanding of the roles of quarks in the structure of the proton. Have you? But gluon structure is far harder to understand, since it's notoriously difficult to measure or calculate. For those who don't know, gluons are what keeps the things together. So you have particles. Don't even say that. Dave, don't say that. We have quarks, whatever the heck that is, being held together by gluons, whatever the heck that is. And what is this concept? Think about it, folks. What is this concept of gluons holding quarks together? Would they hold hands? Are models outside the mainstream, including ether models, which they're based on a lot of wave stuff, like a Jeff Yee. Look at Jeff Yee. Or a particle model. Look at our model, particle model. Or a lattice model, which we have some people working on those. They actually try to answer these questions. They don't just make these arbitrary statements about these things. It's just amazing. A gluon shift. Boy, that sentence being parsed, it could mean a lot of things. Instead of measuring a proton's pressure using particle accelerators, Shannon and Detmold looked into gluons, looked to include gluons' roles by using supercomputers to calculate the interactions between blah, 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 blah. Okay, now they calculated them. They didn't have the computer go look and see, hey, is there some pattern that we humans can't see across millions, billions, trillions of these data, this data of smashing things together. So it says inside a proton there's a bubbling quantum vacuum of pairs of quarks. Do you see this, guys and gals? Do you see this? Listen to this. There's a bubbling quantum vacuum of pairs of quarks and antiquarks, as well as gluons appearing and disappearing. Listen to this. They write these down. This is what they write. And a bunch of intellectuals, not critical thinkers, intellectuals are those people who want to be smarter than everybody else. It's a social thing. It's not a science thing. That's one of my conclusions I've come up with when I was making my movie Einstein Wrong. These people are living and they are talking about this stuff as if it's real, without any physicality. Our calculus include all of these dynamical fluctuations. To do this, you got to hear about how they do it. I'm going to do a whole video on this next part. To do this, the team employed a technique in physics known as lattice QCD for quantum chromodynamics, which is a set of equations that describe the strong force, one of the three fundamental forces of the standard model in particle physics. Used to be four. And then the other two are the weak and electromagnetic force. The strong force is what binds quarks and gluons to ultimately make a proton. The whole thing of the lattice QCD I'm going to talk about. I don't know how much in this one, but oh my goodness, you want to get your mind blown, look it up and read it. I'm going to do that for you, so stay tuned. Lattice QCD calculations use a four-dimensional grid Grids are three-dimensional. Where's the fourth dimensional come in? Oh, because it's time? No, it's a grid over time that has things moving in it, maybe? Oh my goodness. Or lattice of points to represent the three dimensions of space and one of time. I don't know. I don't know enough about these things, even though I work for a company that we make supercomputers, open source. You can go get it. And is it the case that they are actually like making these mathematical equations where they stick this in and they don't use it in the real world like the universe would be, which would be a three-dimensional lattice with things happening over time? But it doesn't seem to be that. It seems to be 4 dimensions, which means to me as a mathematician, which I am, that you would place in the equations time, and that makes part of it as sort of like another dimension. It's not described. The research calculates the pressure inside the proton using equations of quantum chromodynamics defined on the lattice. It's hugely computationally demanding. So we use the most powerful supercomputers in the world to do these calculations. Is that like I'm at MIT, I'm using the most powerful computers? It must be right. You can build a Large Hadron Collider and actually get nothing out of it, which we have. Go Lost in Math, read it. The team spent about 18 months running various configurations of quarks and gluons through several different supercomputers, then determined the average pressure at each point from the center of the proton out to its edge. Okay, that's pretty cool. And I said, like, I think we need to get a hold of this data. It's going to tell us something about their interpretation of it. Oh, compared with the Jefferson lab results, Shannon and Detmold found that by including the contribution of gluons, the distribution pressure in the proton shifted significantly. Now, again, when a person's reading this, they're just assuming that all this stuff is real. They're assuming quarks are facts, gluons are facts, and all these things that they're doing are facts. And the mathematics they put on top of that, they're just too smart. They couldn't be doing all this. This couldn't be a house of cards. This isn't people playing in a unicorn world or in the flat Earth society making calculations that we know are bogus. It can't be that. Yes, it can. We've looked at the gluon contribution to the pressure distribution for the first time, and we can really see that relative to the previous results, the peak has become stronger, and the pressure distribution extends further into the center of the proton, Shannon says. In other words, it appears that the highest pressure of the proton is around blah, 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 and 10 times that of a neutron star, similar to what the researchers at Jefferson Lab reported. The surrounding low-pressure region extends further than previously estimated. I don't have a lot to say about this because why would I talk about the logical explanations of unicorns' migration habits and things and get into their own logic, or even in the logic of Harry Potter, which has its own set of rules and the wizard rules that they have, and getting the argument. That's fun because we know it's all baloney, but in this case people are doing this, and the whole idea is to make this sound as if this is all real, folks, and it isn't. So I think this is the last slide, the end of this. My goodness, thank goodness. Confirming these new calculations will require much more powerful detectors. You notice that too? There they go again. How many times do I tell you? We got to build bigger ones. This is we've got to put more money into it. The problem isn't this stuff is unintelligible because we're illogical. The problem is we don't have big enough toys and not enough money, so keep sending it to us. Such as an electron-ion collider, as proposed as a proposed particle accelerator that physicists aim to use to probe inner structures of protons and neutrons in more detail than ever before, including gluons. Of course, just throw out the gluon part, but it's and then probably the neutron too. We know there's a nucleus, so we'll just say the nucleus. So sending making an ion collider for that. But of course, with their system, it's for naught. But for us, it could be very interesting. We're in the early days of understanding quantitatively the role of gluons in the proton. That's scary. I hope you're not. I hope you're just part of the flat Earth or geocentric instead of heliocentric solar system, folks. I hope this is the last of this craziness. By combining the experimental measured quark distribution With our new calculation of the gluon piece, we have the first complete picture of the proton's pressure, which is a prediction that can be tested at the new collider in 10 years. Man, I tell you, this is the sort of thing, this is like a pyramid. Hey, this is what it is like. I have to remember this, folks. Take a note. Tell David to make this is like a pyramid scheme. Particle physics is like a pyramid scheme. You keep building stuff, you get people to believe it, to capitulate, even though it's totally illogical, even though common sense drives most of the best physicists, mathematicians, and best scientists away from these, and leaves sort of these people who are easily influenced, and they don't really care if it's true or not. That's who run these particle accelerators, folks. I'm sorry, but ask Dr. Alexander Unsker, who is a physicist in Germany. He has come to the same conclusions because he talked to these people, and when you talk to them, they're not like the people that if they weren't in there, they'd be Elon Musk. No, these are people, I was going to go into dentistry but decided to go into particle physics, literally. And they get into it and they just self-perpetuate themselves. How many of those things that we know go on in universities? It's just self-perpetuation. That's what it is. It's a pyramid scheme. You get them in, and that pyramid scheme, you got to get more and more people, and then you got to get more money for that pyramid scheme. That's all this is, folks. And it says, with our new calculator glue, so the next collider, the next 10 years. And of course, read Lost in Math. That is a book by Sabine Hoffenfelder, and she talks about this exactly, and that the Large Hadron Collider was supposed to show these incredibly multi-dimensional universes, like 50 or 100 different crazy ideas, and none of them were shown to be true. And she got disenchanted and left. But yeah, I'm afraid to tell her even that what you think is good that isn't even good. So hopefully you guys are getting the idea and understanding where we're coming from as critical thinkers. And remember what I say, don't take my word for it or anybody else's. Stay critical, stay thinking. I'm David D. Hilser. I'm your science therapist, trying to keep you or make you become science woke. Ciao for now.